If you look at a standard two-story suburban home from the street, you are looking at over 100,000 pounds of building materials and furniture suspended 20 feet in the air. That is 50 tons of downward force. And in almost every modern house, every ounce of that crushing weight is held up by nothing more than simple wooden 2x4s and steel nails. If you have ever watched a renovation show, you have heard people casually throw around the term load bearing wall like it is an optional divider you can knock out with a sledgehammer on a weekend. But behind your drywall, your house is fighting a non stop battle against gravity, wind loads, and ground movement. The only reason your second floor bathtub has not crashed through your kitchen ceiling is a precise, unbroken physical chain called the structural load path. To understand how a wooden frame stands without buckling, you have to realize that gravity never takes a break. Every pound of weight at the peak of your roof must travel through a continuous highway of lumber all the way into the solid ground. The moment that highway is cut or improperly supported, the weight does not disappear. It concentrates into high-stress pinch points that crack foundations, sag ceilings, jam doors, or trigger progressive structural collapse. The journey starts at ground level where the wooden frame meets the concrete foundation. Because concrete is porous and wicks moisture out of the soil like a hard sponge, placing regular framing lumber directly onto bare concrete causes it to rot within a few years. That is why builders bolt down a specialized layer of pressure-treated lumber called the mud sill or sill plate. Underneath this mud sill sits a foam gasket called a sill seal, creating an airtight barrier that stops cold drafts and moisture from creeping under the walls. Every few feet along the perimeter, heavy steel J-bolts are embedded deep into the concrete when the foundation is poured. These bolts run straight through the mud sill and are torqued down with thick washers and nuts, anchoring the entire 50-ton structure so high winds cannot slide the wooden house off its foundation. Sitting directly on top of that anchored mud sill is your home's floor framing system. Long horizontal beams called floor joists run parallel across the span of the house, spaced 16 or 24 inches apart. The ends of these joists are capped and locked together by a vertical rim joist, preventing them from rolling over on their sides under heavy loads. While older homes used solid cuts of dimensional lumber like 2x10s, modern construction frequently uses engineered wood I-joists or open web floor trusses. These engineered joists use solid wooden flanges glued to a vertical OSB web, allowing builders to span massive open living rooms without interior support posts while using far less raw timber. Across the top of these floor joists, builders glue and screw down thick sheets of tongue and groove subflooring. Fastened in a staggered pattern, this subfloor acts as a giant horizontal diaphragm. It locks the individual joists into a single rigid surface that prevents twisting and transfers lateral wind forces across the entire footprint of the building. Once the floor platform is ready, framing crews build the walls flat on the deck and tilt them upright. Every wall starts with a horizontal sole plate nailed through the subfloor into the joists below. Rising vertically from this plate are the wall studs, which act as slender wooden columns carrying downward loads. Almost every residential wall uses studs spaced exactly 16 inches on center. That 16-inch measurement aligns perfectly with standard 4x8 foot sheets of drywall and plywood while distributing downward weight evenly, so no single stud bears an excessive load. At the top of the studs, builders nail down a double top plate. This serves two vital structural functions. First, it acts as a continuous wooden beam, distributing downward point loads from the roof trusses evenly into the studs below, even if a truss does not sit directly over a stud. Second, the upper plate overlaps the joints of the lower plate and interlocks at every corner where two walls meet. This overlapping double plate ties the entire perimeter of the house together into a continuous rigid ring, ensuring that if strong winds push against the front wall, the side and rear walls immediately share the structural resistance. Now, if a house was just a solid box with no openings, framing would be remarkably simple. But homeowners want windows, doors, and hallways, and every opening requires cutting away the vertical studs that hold up the floor and roof above. This is where DIY renovators make catastrophic mistakes, because you cannot simply saw through 2 or 3 studs without creating a structural bridge to carry the load around the opening. That structural bridge is called a header. A header is a heavy horizontal beam, built by sandwiching pieces of 2x10 or engineered LVL lumber together, placed directly across the top of the opening. When weight presses down from above, short vertical cripple studs transfer that load straight into the top of the header. The header redirects all that downward weight horizontally across the opening and dumps it into specialized vertical studs on either side called jack studs or trimmers. These jack studs are cut shorter than standard studs, so the header rests directly on top of them, supporting the downward force entirely in solid compression all the way to the floor plate. Right beside every jack stud sits a full-height king stud running from the bottom plate to the top plate. The king stud provides lateral stiffness, keeping the wall plumb and preventing the header from shifting. Below a window opening, horizontal sill plates and lower cripple studs transfer the weight of the window unit down to the bottom plate, completing a rigid four-sided frame that channels gravity safely around the void. This brings us to the most critical distinction in home anatomy: the difference between a load-bearing wall and a non-load-bearing partition wall. A partition wall is essentially a room divider. It supports nothing other than its own drywall, and you could remove it without threatening the structural integrity of the home. A load-bearing wall, on the other hand, is a vital link in the gravity load path. These walls typically run perpendicular to the floor joists or roof trusses above them, catching the ends or midpoints of those framing members and transferring their weight down through the structure. In a two-story home, load-bearing walls stack directly on top of each other, aligning with heavy steel I-beams or timber girders in the basement supported by steel teleposts. If an inexperienced renovator cuts into a load-bearing wall without first installing temporary support walls and engineering a structural replacement beam, the results are immediate. The floor joists above will sag, drywall seams will tear across the ceiling, floors will become bouncy, and interior doors will stick in their frames because the openings have warped out of square under extreme mechanical stress. Moving to the top of the structure, we reach the roof framing, which carries not only the dead weight of plywood and shingles, but also live loads from winter snow and upward suction from high winds. Modern homes almost exclusively use pre-engineered roof trusses manufactured with computer-calculated engineering models. A roof truss works on the geometric principle that a triangle is inherently rigid and cannot deform without bending or breaking one of its sides. The sloped top chords are placed in extreme compression as gravity pushes down on the roof. The horizontal bottom chord is pulled in extreme tension, acting like a structural tie rod that prevents the exterior walls from being pushed outward by the roof's weight. Inside the truss, an internal network of angled webbing members transfers forces back and forth between compression and tension, and every joint is locked together by heavy-gauge steel gusset plates pressed into the wood fibers. Where roof trusses land on exterior walls, builders install galvanized steel brackets called hurricane ties. When high winds blow over a sloped roof, air rushing over the peak accelerates, creating a low-pressure aerodynamic suction zone that literally tries to lift the roof off the house like an airplane wing. Hurricane ties wrap around the roof truss and nail into the double top plate, ensuring wind uplift forces are anchored directly into the weight of the entire wall system below. Finally, a home must defend against lateral shear forces. If a house only had vertical studs and drywall, strong winds blowing against the side of the building would cause the entire rectangular frame to rack and fold flat like a cardboard box. To prevent this, builders install structural sheathing, usually half-inch thick oriented strand board, nailed to the outside of the wall, framing in a precise, engineered nailing pattern. When these large 4x8 foot panels are nailed every 6 inches along the edges and 12 inches in the field, they convert flexible vertical studs into rigid shear walls. These shear walls absorb lateral wind energy pushing on the exterior, convert it into diagonal shear tension, and transfer that load safely down into the floor diaphragm and anchor-bolted foundation. Understanding this continuous chain of wood, steel, and physics is why professional builders treat framing with absolute precision. Even small modifications made by other trades can compromise the entire system if done incorrectly. For example, when plumbers or electricians run pipes and wiring through floor joists, building codes strictly regulate where holes and notches can be cut. When a floor joist bends under weight, the top half of the wood is squeezed in compression, while the bottom half is stretched in tension. Dead center along the height of the joist is the neutral axis, where stress is virtually zero. That is why drilling a clean hole through the exact center of a joist maintains almost all of its structural capacity, whereas cutting a deep notch out of the bottom edge cuts the wood fibers where tensile stress is highest, instantly ruining the board's load rating and inviting a catastrophic split. From the steel anchor bolts embedded in the concrete footing, through the floor diaphragms, studs, headers, and shear panels, up to the engineered triangles of the roof trusses, your home is not just a collection of separate rooms. It is a single, interconnected structural machine designed to balance thousands of pounds of force 24 hours a day, keeping you safe and dry under a roof that stays exactly where it belongs.